So in our first module, we touched on some things, and you had a very, very minor thing to do. And basically had to open up in the virtual machine, and if you couldn't import the virtual machine appliance, you could just load Ubuntu. And in just a second, we'll have a screen, but basically, you'll see that we have oh, come on now. There we go. So one thing that's nice about having the PG Book appliance is that PG Book appliance includes a terminal link on the side. But if you're using Ubuntu without importing the PG Book, if you just set up a virtual machine with Linux instead, you can click on search and then type terminal. And an option to start a terminal will show up on the screen. And so for your first solution, you basically had to issue a single command inside the terminal to create some output. And when you're working with data files, you need to be able to do some things if a canned prefabricated solution is not available. And so we're going to get a lot further into the second chapter. One of the intents of our second module is to start working from the command line interface, or terminal prompt, as some might call it, or command prompt, right? In Windows, if you're looking in Windows, there's a lot of things that you can do from inside the command prompt of a Windows machine that work very much like the Linux machine. But on your assignment from yesterday, we ask you to read the Wired magazine article about the paradox of bad software. And I was really struck by this article. I saw it some time ago, and I thought this would be ideal for our 239 Scientific Computing Applications class. And so, you know, the author talked about all of the different ironies. Computer science is part of the discipline in STEM, and you'd think that scientists would have more. So in a sense, the article speaks to the need for a class like Scientific Computing Applications. How do you post credit or log credit for your submission? Well, if you just responded to the prompts and provided your own answer about the notion or concept from the author that you thought was most relevant where you sit, right? So for where you are as a STEM undergraduate, you know, how is this article relevant? And if you just explain a little bit about that, then that's half of it. And then here's the part that I was floored with. I read this article, and then I thought, what's ignored? What is this author ignoring? I don't know. Could be the fact that every STEM undergraduate should have a class like Scientific Computing Applications, where you learn to create your own custom applications. So yeah, he's talking about the supply and demand side. He's talking about the industry. The one thing that I want to call out is another undercurrent of irony here. And it's all about the fact that, you know, if you engage the right kinds of courses and get up to speed on certain skills, you build your own. I would like to see which environments the author was playing in. The point is, your textbook author also goes to a lot of trouble to make sure that you have the tools so that you start to understand how to work. Now, I want to caution you, when you follow the textbook, you're going to see a lot of hairy, scary stuff. And what I mean by that is, you get further into your textbook and it starts talking about the command lines. Yeah, the first part of it's not that big a deal. But one of the things I want you to understand is that you can tell where you are because there's a convention where the prompt is, the login should say PG book and PG book, right? PG book VM. And so all of that is pretty straightforward stuff. The idea that you can use a manual command or man command with any other command to get an online manual is important to understand, because you have to be able to find the information to use commands and tools. And part of what happens with scientific computing applications is that you'll find one utility or one software will do part of the data crunching, part of the data management, part of the data analysis, but it won't do the rest. And oftentimes when you're working with scientific computing apps, you have to stitch them together. You have to write a script to load one after the other. The first one runs a process that generates the data file and stores it. The second command imports the data into a second application, and so on. So you have to be a little bit familiar with some of these things. We issued the ls-al command for your first solution, so we could get something that looks like this. But what I want you to do now is to go through the textbook and try all of the commands that the author intends for you to learn, especially when it comes to file names and conventions, so the case sensitivity and so on. You do need to understand that some of the characters, people run into problems because they're in the wrong directory. When we're working in Linux, much of the time a command does not work. It's because the resources are not housed or located in the same folder. So right now, I use the pwd command to show me which working directory, print the working directory, and I'm in home/pgbook, right? So that's the directory I'm in right now. If I issue a command to do something that doesn't live in this folder, I just listed everything in the folder. If I try to run something that isn't in this folder, I'm going to get a command not found. This happens constantly in Linux. And a lot of times, if you just navigate around in the different directories and then repeat the same command, things work very nicely. But I want to make this easy for you. So if there's a command in the book for the rest of chapter 2, I want you to know it. I want you to work with it. I want you to get on the screen and do. Here's a simple command to redirect the output of a list and create a file called directory out. So we're going to do that right now. I want you, between now and next class, to get into your screen on the terminal, just like I am. And I want you can move this so that you can see what you're doing here. I want you to do the same things that you see in the textbook. I'm going to redirect, and then I'm going to directory.out. Now if I look If I look in this directory here, inside the listing, I don't have a file called directory out. But it's helpful to know that if you just hit the up arrow key, you can repeat previous commands. So I'm going to hit the up arrow key a time or two. So I can repeat the command. And now if I look, I have a file called directory out that didn't exist before. And if I want to be able to display the contents of that file, I'm going to use the cat command. So if I contents of the contents of the directory out file was a listing of files. So all I did was take the output of the directory listing command, ls command, and store it in the directory command. So you need to play around and get used to the idea that you can, malleable is the term that comes to mind. You want to be malleable, even though we're used to a GUI, we're used to clicking on this and going into a file structure. And I got to be honest with you, sometimes what you need just can't be done in a GUI. It's not in a Mac environment with a slick interface where you can click and drag and drop and all that kind of stuff. Everybody needs to get more familiar with this kind of stuff. And as long as you take it slow, you can you can eliminate a lot of headaches. Here, the same command, if your key bounces, instead of just capturing and directing the output of that command to this file, I can redirect other content to directory out. So to demonstrate, I'm going to take the pwd command and I'm going to append it to directory out. You'll see the last line of directory out that's displayed is this line here. But what I'm going to do is take the pwd command and I'm going to append it. I'm going to append it to directory out. And that means I'm not going to overwrite it. I'm going to add it, the last line. That's an important distinction because there's a lot of processes in the Linux environment that we're doing to collect data. When we're appending to a data file, we're not overwriting the data file. If we use a double arrow, it appends. If we use a single arrow, we're screwed because we keep rewriting our results over and over and over again. Those distinctions are important to understand. So if I'm going to do this, and I go ahead and click into the window here, and then I hit enter, and now let's display the contents of that directory. What I should see is this last line, and then home PG KVM, right? That's what I should see. And that's what I see. So as I display the contents of directory.out, here's the last line I saw before, but now on a new line over on the left is the output of the pwd command. I have appended it to the directory.out command. Are there any questions about the example we've covered from the textbook?
No, not yet.
Okay. In your study guide, let's look at the study guide. So I want you to learn what's in the Linux command cheat sheet that's also going to be posted inside Module 2, and it covers a lot of different commands. And so I want you to basically it's not a very long document, but I want you to try those, and I want you to try the ones from Chapter 2. We're going to be using those in programming and coding methods for the solution. So you need to start becoming familiar with those. We also, whoops, in your study guide, one thing I want to make uh, easy for you, just as before, if it's something that's shown in the study guide, man, you better memorize it. So basically, if you read something like this in the study guide that says, take the greatest of care whenever you use rm space -r with any wildcard symbols, that's the Linux command for remove or delete. And -r means recursive. It means do it in this directory and in the subdirectories and all the other directories. Depending on the extra characters that follow, if you don't know certain commands, you can hose your entire Linux virtual machine. So I explained some things by section, what you should know. And if I call it out in the study guide, you need to learn about it. You need to make sure you know it from the textbook, and you need to try it in the virtual machine. Okay. So, here's an example from page 32 of the textbook, right? Midterm.dat. It's important to understand the difference. If you see control dash, if it looks like it's a -1, sometimes it's an L. So we're calling those distinctions out differently. There's a difference between a backslash and a /. If your shell or terminal gets stuck, you can use those key combinations to get out. So once again, this is pretty basic stuff, and it's pretty self-explanatory, and it's easy to read and understand in the textbook. But I want you to know that there's an expectation that you log the time to finish the rest of Chapter 2 and the Linux cheat sheet and the study guide, and you get up to speed, because on Tuesday, we are going to review the steps and the tasks one after another for your solution. Are there any questions about what we've covered so far?
So all we have to do is finish chapter 2 on our own and be prepared for Tuesday.
Yes. I'm going to post some other things. There will be a YouTube that you watch. There will be some quick some quick posts for other resources, but yeah, that's pretty much it.
Okay. All right.
If you don't have
Question.
the textbook yet, now's the time to get it. And if you still were trying to finish up getting some kind of Linux machine working, I do have some good news. If you've struggled with a laptop that isn't running the virtual machine, for those of you who are Mac users, if you want to run the PG Book VM, you can sign a laptop out for the semester from the library, Dell laptop with a nice processor, 8 gigs of RAM, large hard drive, and the version of this thing for Windows works nicely. So if anyone in class is interested in picking up a laptop to work the rest of the process, you've been wringing your hands and frustrated trying to get some things set up on your own system, I wanted you to be aware. I just learned that that's an option. The other thing that I want you to know as well is that everyone should have Access installed. So what am I saying? Everyone has a laptop, and when you install Access from the campus Office 365 option in the portal, that installs Access for databases. So another thing that everyone needs to do to get ready for Tuesday, and that's going to be an assignment, is that you show me that you have access on your system. Now, what do you do if you don't have access because you have a Mac? The Office 365 version you can download and install may include that, but you want to be able to open up a blank database screen and create a new database. So we'll be working with data, command line, writing some code, and working in Access. And for all that to happen, you have to have access to Access. I know that sounds kind of corny, but so it would be good if you were to check your laptop now, as in right now. Some of you had Office installed when you purchased your laptop and it was included, but it might be a standard edition of Office that does not include Access. So it would be good to know. You can run Access and install Office inside a virtual machine using Server 2019. So for those of you that downloaded, if you wanted to go that route, you could. But once again, an easier fix might be to just pick up another laptop from the library. You can sign it out for the entire semester. So what are you going to be doing for your solution? One of the things you'll be doing for your solution is to build out a database. We want you to work with data, and one of the things that I'm going to step through is the creation of a turtle sightings database. So there's a YouTube video and it shows you what to do, but you're going to build some data tables to contain data sets. And so these are two tables called Sightings and Species Lookup. And they're named based on their purpose, and there's a lowercase t, so I'm using sensible names. So self-documenting, I'm self-documenting. I'm going to use a name that has something to do with a purpose, and it's going to tell you something about the object. This is a database table, that's why there's a lowercase t. When I do queries to sort or to analyze the data, I'm going to start that database object name with a Q, so I know that in the listing, if I have a form, it's a form, F for form, T for table. And so this is an example of an open database table. So I have a sighting table with a turtle name, turtle species ID, sighting ID. We'll cover all of that in the YouTube videos and on Tuesday when we review for the solution. But in order to work this environment, it's actually a very straightforward process. And in order to understand how to structure data so it's useful for analysis, the best way to understand and learn that is to actually walk through an example. So we did mention in the previous module that if you have several data sets and there's related data elements, like here there's a turtle species ID in the species lookup table, and in the sightings table we identify what species the turtle is. It's a very efficient, very easy to set up. It's not a long or lengthy process. But you'll notice here there's a relationship established between these two tables. And you're going to have some reading that has to do with database relationships. So later in the reading, it's going to talk about relationships or joins, query types that you can set up. And in the textbook, it talks about types of joins that include all records that are common, right? So this is another way to look at it. Another reason why we want to have access in front of you is because as you're reading the textbook, you're going to roll your eyes and say, oh my gosh, what is this? What is this man saying? What are these authors saying? Some of the material, when you get into the database piece of it, it's talking about relational algebra and how you relate data sets together and how the tuples are common between or not common between, and that gets very complicated. I want you to know that if you read something in your textbook and then come back here and look at join properties, it's probably a lot easier to understand because it's stated in plain English. Oh, here's one type of query: only include rows where the joined fields from both tables are equal. Oh, here's another type: include all records from this table and only those records where the joined fields are equal. Or include all records from sightings and only records from the species lookup that are equal. So if there are distinctly different records that don't match, those are excluded. So that's one of the criteria of a join that's described in your textbook. And it makes a lot of sense to look at it in context or to try an example out for size. You have other joins that exclude duplicate records. You have two tables, you have duplicate records. You might have another join and a relational algebra interest where you want to execute a query, and what you want to generate are the records that are not common. So the output, you don't want to identify and output all the records that are identical between the two data sets. You want to identify and output all the records that are not the same in each of the data tables. And so once again, that's something you want to start reviewing and reading, but then you want to have this context and access. You want to look up something in the textbook about the database. So we look at later on in organizing data, relational algebra. This is where we start getting into the fun stuff. So we talk about data modeling. This is also part of our module here. They'll start talking about, and they'll use examples about auction data. You created some in an Excel spreadsheet. We're going to use that. It talks about how the elements of the data that you need for the analysis are related, and it has a diagram here. And in terms of relational algebra, that's called an entity relationship diagram. Looks like a flow chart, really. When you go ahead and start working with relational algebra, this gentleman named Codd is like the Einstein of databases. He's the one that first codified, ironic, codified relational algebra and how database stuff comes together. But in the relational algebra section, it starts talking about query language. And one of the things I want to call out are some of the examples and the diagrams in particular. So they talk about the different kinds of joins, union joins, and here's some diagrams to try to explain some of that. So on Tuesday and Thursday of next week, we're going to call out some of these specifics, but you need to start reading. So, you know, it takes a while to get into, but it's talking about how you have common elements between the two tables. So between the left table and the right table, you have B1 and B3, and over on the right table, you have B1 and B3. So joins are going to discern specific criteria based on the nature of the join. The most important things I want you to understand are the most common ones. So in the study guide, we talk about the most common joins in SQL data. So it'll yield all the records in a database that are present in both table 1 and table 2. So once again, we're borrowing from different contexts to help decipher the content here. With this kind of join, a union join, it'll yield all tuples present in either table 1 or table 2. The second kind of join will yield the records that are present in both tables. And in the third case, the records that are present in the first table but absent in the second one. So the diagrams that are used to explain this, we're going to review that further, and we're going to give you some more examples. But you're going to want to have access available. You're going to want to get into this application, and after we refer to certain things in the textbook and in the study guide, we're going to open up access and explain all that.